So let's get back to this example. Again, an example. This example will give us an idea how we can use the criterion for phase equilibrium to know phase conditions. This one says, in specifying molar Gibbs free energy of a compound, the liquid phase at 300 Kelvin and 100 kilopascal is being used as the reference state. Once you hear this word, then I'm telling you that molar Gibbs free energy, or whatever criterion that you will use to calculate phase equilibrium conditions at this condition, assume it to be zero. Okay, this is what here it says clearly, that molar Gibbs free energy is zero at this temperature and at this pressure. So if I didn't put this sentence, but I only give you that this condition is the reference state, so this means the molar Gibbs free energy is zero. If you are working with fugacity will be zero. So whatever criterion at this reference conditions, assume it to be zero. Clear? Okay. It has been estimated that we have pure vapor at 300 Kelvin, 100 kilopascal. Gibbs free energy for the vapor at this condition is 500 joule per mole. Okay. So at this condition, like 300 Kelvin, 100 kilopascal, do you think now we have phase equilibrium condition or no? Again, compare molar Gibbs free energy for the two phases we have, for the vapor, for the liquid. So here, at liquid phase, this is the reference state, so molar Gibbs free energy for the liquid at this pressure, at this temperature is zero. At the same pressure and temperature, molar Gibbs free energy for the vapor are 500. So molar Gibbs free energy for both phases are different at the same pressure and temperature. So this temperature and this pressure are not representing phase equilibrium conditions. There is no phase change will happen at this one. So now he wants to calculate the value of Gibbs free energy at 300 Kelvin at 1 kilopascal relative to the reference condition. Calculate molar Gibbs free energy for 300 Kelvin, 1 kilopascal relative to the reference state. So now I'm giving you same temperature, same pressure, calculate Gibbs free energy for liquid, calculate Gibbs free energy for vapor. And then I can ask you, do you think that 300 Kelvin, 1 kilopascal, this is the phase equilibrium condition or no? So the key here, calculate Gibbs free energy for liquid, molar Gibbs free energy for vapor, compare them. If they are equal, so this is the condition of phase equilibrium. Not equal, this is not the condition for phase equilibrium. Another question, calculate vapor pressure at 300 Kelvin. If 1 kilopascal is not the vapor pressure at 300, so what will be the vapor pressure at 300 Kelvin? What will be the pressure at which phase change will occur at 300 Kelvin? Okay. So how we can solve this problem? So the easiest way to solve this problem, what is happening? Okay, is the following. So put the given information here. So we have liquid. This liquid at, I forget the condition. Okay, 300 Kelvin. And 100 kilopascal. At this condition, molar Gibbs free energy for liquid is zero. We have vapor at 300 Kelvin, 100 kilopascal. Molar Gibbs free energy for the vapor phase at this condition is 500 joule per mole. The first requirement says if we have liquid phase and we have temperature 300 Kelvin, we have pressure 1 kilopascal, what will be the molar Gibbs free energy for the liquid at this condition? And again, based on the given, I know that if I have liquid, this liquid at 300 Kelvin, at pressure 100 kilopascal, the molar gaps free energy for the liquid at this condition is 0. So again, this is the given. And this is the condition that I need to calculate. And this is the requirement condition. If you can calculate the change in the molar Gibbs free energy, then we can calculate Gibbs free energy at the final state. Make sense? Okay. So how we can calculate the change in the molar Gibbs free energy? So again, do you remember chapter 6? The total derivative, the triple product, the expansion rule, all of these rules. So we can start. So now we need to recall chapter 6. And we can say the change we have in molar Gibbs free energy equal dg by one variable plus the partial change of molar Gibbs free energy with respect to another variable. What are the two variables? Two easy variables you can select to calculate the change of molar Gibbs free energy with respect to these variables. Temperature and pressure, because they are given. Okay, so here we can calculate this one, change of molar Gibbs free energy with respect to pressure at constant temperature, and dg by dt with respect to pressure dt. Okay. Okay. So again, if we use the fundamental property relations, Maxwell relations, all the stuff we have did for the previous chapter, then we can say dg is vdp minus sdt. So again, if we recall the fundamental property relations, you will see that dg by dp at constant temperature, this is equivalent to molar volume. And if you calculate dg by dt at constant pressure, this is minus entropy. Okay? Okay. So now compare these two things. I have temperature initially at 300 Kelvin, final 300 Kelvin. So do you have any temperature change here? No, temperature is constant. So this is why this term will be cancelled. Because T1 and T2, both of them equal 300 Kelvin, then dt equal to 0. So the change we have in molar Gibbs free energy is VdP. So now we can integrate this equation. Then delta G, which is G2 of liquid at the case number 2 minus molar Gibbs free energy of liquid at case number 1 equal the integration from the first pressure to the second pressure molar volume dP. Clear? Okay. So this molar volume, this is volume of the liquid, because in this requirement I have everything in the liquid phase, and liquid are incompressible. So the volume of liquids are not changing with pressure change. So we can assume that this molar volume can be assumed to be constant. And since it's constant, it will be out of the integration. Then we can say the change we have in molar Gibbs free energy, which is again molar Gibbs free energy at case number 2 for liquid minus molar Gibbs free energy for liquid at condition number 1 equal molar volume of the liquid phase times P2 minus P1. Okay. Then we can put the given information here. Then molar Gibbs free energy for the liquid at second condition minus molar Gibbs free energy at the first condition is 0 equal. The molar volume is given in the problem is 125 centimeter cube per mole. So this will be 125 centimeter cube per mole. So I need to convert everything to the SI system. So this will be times 10 to the power negative 6. So again, this one is given. In centimeter cubed per mole, and I use this one to convert centimeter cube per mole to meter cube per mole. Then we have the pressure. Pressure at the final condition is 1 kilopascal. Pressure at the first condition is 100 kilopascal. Again, kilopascal. This is not SI system, so I need to convert it to Pascal. So I will multiply to 10 to the power 3. So 10 to the power 3, this one, convert kilopascal to Pascal. So now I have everything is in this SI system. Okay, all the information is now given. I have only one unknown, which is molar Gibbs free energy for the liquid at 300 Kelvin, 1 kilopascal. So calculate this one, and then I can say molar Gibbs free energy for liquid at second condition will be negative 12.4 joule per mole. And this is the first requirement we need in this problem. Clear? Okay. Second requirement, calculate molar Gibbs free energy at 300 Kelvin, 1 kilopascal, but this time for the vapor phase. Okay, so what we will do in this problem, this is the second requirement. So B, I have vapor phase. So I have given that at 300 Kelvin, at pressure 100 kilopascal, molar Gibbs free energy for the vapor at this condition is 500 joule per mole. So this is the given. And the required at 300 Kelvin, pressure 1 kilopascal, what will be the molar Gibbs free energy for vapor at this condition? So we'll do the same. Again, we have total derivative, substitute in total derivative from chapter 6. Then we have dg is VdP. But this one, this is volume of vapor, not liquid. So integrate this equation. So we can say by integration, then the change of molar Gibbs free energy, which is change or molar Gibbs free energy of vapor at case number 2 minus molar Gibbs free energy of vapor at case number 1 equal integration from the initial pressure to the final pressure, molar volume of the vapor dP. Now this is vapor. Can we assume the molar volume constant? No, we cannot assume molar volume is constant, okay? Because this is vapor. So again, this one cannot be assumed. as constants because vapor are compressible. Okay. So one of the things here also we can do that. So in this problem we have low pressure. And once you have low pressure, then you can assume what? Ideal gas behavior. And then we can use the ideal gas equation of a state, PV equal RT, or if we rearrange this equation, so the molar volume is RT over P. Then put this now in the equation, then we have delta G, change of molar Gibbs free energy, molar Gibbs free energy of vapor, case number 2, minus molar Gibbs free energy of vapor, case number 1, equal integration from initial pressure to final pressure RT over P dP. Or this is constant, temperature is constant, case number 1, case number 2 have the same temperature. I can put them out of the integration, so this will be RT integration from P1 to P2 dP over P, and this will be RT ln P2 over P1. Then let's put all the information here. So then molar Gibbs free energy for vapor at case number 2 minus molar Gibbs free energy of vapor case number 1 is given 500 joule per mole. It's in SI system, there is no need to convert any units, equal R ideal gas constant 8.314 joule per mole Kelvin, no need to convert this one. Temperature is given 300 Kelvin, ln P2 over P1. Since P2 and P1 are divided, then there is no need to convert the units because the conversion factor will be cancelled. So P2 is 1, P1 is 100. So everything is given in this equation. Then we can say G2 or calculate molar Gibbs free energy for vapor will be negative 11 thousandths joule per mole. And this is the second requirement. So now let's compare this. So we have 300 Kelvin and 1 kilopascal. For at this condition, if I have liquid, then molar Gibbs free energy for this liquid is negative 12.4 joule per mole. If I have vapor at this condition, then molar Gibbs free energy for the vapor at this condition negative 11 thousandths joule per mole. So now since molar Gibbs free energy for both phases at same condition are not equal, so this means phase equilibrium will not exist at this temperature, 300 Kelvin and 1 kilopascal. So this is not like phase equilibrium conditions or phase transition conditions. Is this clear? So now the last part of this problem. So how can we calculate, or what is the pressure? Let's assume the temperature is 300 Kelvin. If I keep temperature 300 Kelvin, what is the pressure at which phase change or phase equilibrium will exist at 300 Kelvin? And this is the third requirement. So third requirement, we need to calculate the like vapor pressure, P saturation. Some textbooks, they call it P star. So if you see P sat or P star or Even in some textbooks, they call it PV, vapor pressure, so they are the same. Calculate saturation pressure or vapor pressure at 300 Kelvin. So saturation pressure at 300 Kelvin, so this means at this pressure, at 300 Kelvin, at this combination, we have phase equilibrium exist, right? Phase equilibrium exists, so the rule is if you calculate molar Gibbs free energy for liquid, molar Gibbs free energy for vapor, they will be the same. Okay, so if we get back to requirement number 1, here we have an equation. This equation can be used to calculate molar Gibbs free energy for, or we used it already to calculate molar Gibbs free energy for liquid, right? And here we have an equation, we developed this equation in order to calculate molar Gibbs free energy for vapor. We said it's RT ln P2 over P1. So now these are the two equations I will use. So here I have then from requirement A in this problem, I have this equation. Let's put it. G2 of liquid minus molar Gibbs free energy of liquids at condition number 1 equal molar volume of liquids P2 minus P1. And from requirement B, I have molar Gibbs free energy of vapor at second condition minus molar Gibbs free energy of vapor at first condition equal RT ln P2 minus P1. At phase equilibrium condition, then molar Gibbs free energy for liquid should equal molar Gibbs free energy of vapor. They should be equal, okay? So, so if we start substituting in this one, okay, so if we start substituting in this one, so from this equation, then molar Gibbs free energy of liquid at second condition equal molar Gibbs free energy of liquid at first condition plus molar volume of liquid P2 minus P1. So condition number 1, that temperature 300 Kelvin, pressure 100 kilopascal, molar Gibbs free energy for liquid at condition 1 is 0. This is the given information. State number 2, I know the temperature is 300 Kelvin. I have no idea what is the pressure at this condition, and I have no idea about the molar Gibbs free energy at this condition. So start put all of this information here. Then we can say molar Gibbs free energy of liquid at the phase equilibrium condition equals 0 plus molar volume 125 times 10 to the power negative 6 times P2 minus P1. P2, I have no idea what is P2. This is the pressure I need to calculate. Minus P1 minus 100. And all of this times 10 to the power 3. So this, let's call it, this is equation number 1. Then repeat the same thing for the second equation. Molar Gibbs free energy for vapor at the second condition equal molar Gibbs free energy for vapor at first condition plus RT ln P2 over P1. So again, state number 1, this is the given. I have vapor at 300 Kelvin, and at 100 kilopascal, and molar Gibbs free energy for this vapor at this condition is 500 joule per mole. The requirement, or state number 2, phase equilibrium condition. I only know that temperature is 300 Kelvin, but I have no idea what is the pressure at this condition, what is molar Gibbs free energy at this condition. Again, start put all the information here. Then we can say molar Gibbs free energy for vapor at phase equilibrium condition equal 500 plus ideal gas constant times temperature ln P2 over P1, which is 100. And call it equation number 2. So I have equation number 1, calculates molar Gibbs free energy for liquid phase at phase equilibrium conditions. Okay, at 300 Kelvin and at vapor pressure. I don't know what is the value of this vapor pressure yet. Equation number 2 calculates molar Gibbs free energy for vapor phase at 300 Kelvin and at vapor pressure. So again, the key here that at this condition, molar Gibbs free energy of liquid equal molar Gibbs free energy of vapor. This is the criteria that we have. So now if we since at phase equilibrium, molar Gibbs free energy for liquid at phase equilibrium condition equal molar Gibbs free energy of vapor at phase equilibrium, then from equation 1 and 2, then we can say 0 plus 125 times 10 to the power negative 6 times P2 minus 100 times 10 to the power 3, all of this equivalent to 500 plus 8.314, 300 ln P2 over 100. So we have only one unknown in this equation. The only unknown we have in this equation, this is P2. Here I have P2, here I have P2. Then I can calculate this equation. And then we can say P2, this will be 81.76 kilopascal. And this is the requirement here. So this is the vapor pressure. So we used the criteria of phase equilibrium here in order to find the temperature and the pressure at which phase equilibrium or phase change will occur. Okay, so the simple rule, this criteria, the value of this criteria, which is molar Gibbs free energy or chemical potential, is equal for both phases, vapor and liquid. So I'll calculate, I find one equation for liquid, one equation for vapor, make them equal together. In this equality equation, we have vapor pressure is unknown. I substitute and find P2. So if you have this substance, and if you have 300 Kelvin and the pressure 81.76 kilopascal, only at these pressure and temperature conditions, phase equilibrium or phase transition will occur. Is it clear? Any questions? In the beginning, in the lecture, we said we have a second limitation of using Gibbs free energy. Okay, and this is quickly, this limitation is this. Let's get back to this table. So this table gives you the value of molar Gibbs free energy of liquid, molar Gibbs free energy of vapor at different pressure values. So if you can see here, in this one, again, this is the condition, the pressure at which molar Gibbs free energy are equal. If you can see here, if you have small pressure change, in the first column, the pressure values are very close to each other. We have only small changes in pressure. But even with this small pressure changes, you can see molar Gibbs free energy for liquid is almost constant. 22.8, 22.8, 22.75, 22.5, almost the same. But molar Gibbs free energy for vapor, we have larger changes in this one. from negative 25 to positive 50. This is the second issue we have with using molar Gibbs free energy. If we plot the change of molar Gibbs free energy with pressure, you can see that we will have here a black line. This black line represents molar Gibbs free energy for liquid, and it's almost constant. But molar Gibbs free energy of vapor, it have like significant variation happening. And the issue here, if the pressure becomes very small, the value of molar Gibbs free energy of vapor can reach negative infinity. Or mathematically you can say the limit of molar Gibbs free energy if pressure approaches zero, this is negative infinity. And again, this is for the vapor. And this is the issue here we have with molar Gibbs free energy. So molar Gibbs free energy is an easy criterion we can use. Okay, but again, it cannot be used for mixtures. It can be used for pure substances. But we have one issue, if we will use it for pure substances, that we have possibility that the molar Gibbs free energy for vapor, if you are working with the small pressure values, you have significant variation with small pressure changes, and the value of molar Gibbs free energy can be negative infinity. And this is the reason that leads us to find a new property that we will use this property to calculate or we can use it as criterion for phase equilibrium, and this criterion is called fugacity. And this will be the topic that we will discuss next lecture, is fugacity.